Dawn in Callao. The quiet harbor prepares for another demanding task, welcoming the chemical tanker to dry dock. The gates slowly open, and the vessel Moquegua is guided into position. Watching such a large ship settle on its keel blocks always inspires respect for the precision of naval engineering. The first challenge is the hull. Monks at sea leave it covered with marine growth, small organisms that cling stubbornly and increase fuel consumption. High-pressure water jets blast the surface clean, restoring the smooth lines essential for hydrodynamic performance. The difference before and after is striking, almost as if the ship regains its original energy. Next comes abrasive blasting with copper slag, stripping away old paint layers weakened by long voyages. A fresh surface is prepared for coatings that will protect the steel for years to come. Simultaneously, in the engine room, technicians disassemble the propulsion shaft, polish the propeller, adjust nuts and flanges, and reinstall protective guards. Every part removed and restored adds confidence in the vessel's reliability. Attention then shifts to the cargo system. Since the tanker carries bulk liquid chemicals, stainless steel tanks are inspected down to every millimeter. Experts search for corrosion or wear, ensuring no trace of weakness remains. Their work underlines how safety and performance are inseparable at sea. The hydraulic system, vital for operating pumps and discharging cargo, undergoes testing and maintenance. On the hull, 4 layers of paint are applied, the final being a silicone coat designed to resist new marine growth and meet strict environmental standards. When the dock floods again and the Moquegua floats free, it is more than a ship maintained. It is a vessel renewed, ready for another cycle of demanding service. The first impression of the workshop is the size of the machine itself, built to bend steel profiles of massive thickness. A structure like the AKBEN DAPK 550 instantly communicates the scale of industrial bending, where raw sections of metal are shaped for construction and infrastructure. The weight of the beam alone makes the process feel like a contest between raw force and engineered control. The process begins by selecting a large I-beam, positioned onto the feeding platform. With hydraulic strength, the beam is pushed between 3 hardened rollers, each one applying controlled pressure. Observers often find it surprising how smoothly such a heavy piece of steel can move. The rollers gradually press into the profile. Adjustment of top and side rollers allows operators to regulate the bending radius according to project requirements. Every minor change in pressure directly affects the arc being formed. Next comes the continuous rolling stage, where the beam is cycled back and forth. The repetition of passes shows how shaping steel is less about speed and more about steady force. The machine maintains alignment so the beam does not twist or distort during the process. At this stage, the quiet consistency of movement reflects a balance between mechanical strength and operator guidance. The result is a structural component ready for use in bridges, buildings, or large frameworks. It is remarkable that such strength can be engineered in only a few passes. By combining hydraulics, hardened rollers, and human oversight, the bending machine demonstrates both power and reliability. Strength in modern industry often depends on machines built to handle extremes, and one of them is the CTX Delta 4000 and 6000 TC turning center. These massive systems are designed to work with components for transportation, energy, and aerospace, where size and accuracy define performance. The scale of the equipment alone commands respect the moment it begins operating. With turning and milling spindles combined, they represent a powerful integration of capability in a single frame. The CTX Delta 4000 TC stretches up to 4,000 millimeters, while the 6000 TC reaches 6,000 millimeters, giving them the range to tackle very large shafts. Their spindles accept HSK 100A or Capto C8 tooling, rotating at speeds up to 12,000 revolutions per minute. The drive rating reaches 34 kilowatts with a maximum torque of 260 newton meters, more than enough for demanding cuts. Hearing such figures makes it clear why these machines are trusted in critical industries. A main spindle and counterspindle offer bore sizes of 275 millimeters, powered by 52 kilowatts and generating torque up to 750 newton meters. Speeds reach 1,000 revolutions per minute, ensuring both flexibility and strength in machining. An optional tailstock provides 150 millimeters quill stroke with 6 MT reception, while steady rests, 2 for the 4000, 3 for the 6000, support long workpieces. The adaptability of this configuration ensures uninterrupted production, even on oversized parts. Clamping diameters up to 510 millimeters give secure holding for large materials. The chain tool magazine holds 50 tools as standard, expandable to 100, 140, or even 180, with each tool up to 600 millimeters long and 30 kilograms in weight. Such capacity transforms the turning center into a workshop in itself. Efficiency here is not a slogan, but a direct result of engineering. An exhilarating pulse of human determination bursts forth, stirring a deep awe and respect for the immense effort behind this ship's creation. This is not just construction, it is the celebration of human ingenuity. The video reveals the making of the Canadian Coast Guard's offshore fisheries science vessel, tracing its transformation from design to seaworthy marvel. Preparation of the steel plates initiates the production sequence. The raw components are sorted and measured to open the first phase of work. Once alignment is confirmed, the steel blank takes center stage as rolling commences, and the ship's hull begins to emerge. The blank undergoes initial shaping as it enters the rolling machine. Marking the opening stage in this shipbuilding tale, construction continues through staging and block assembly. Metal sheets pass through the furnace, reaching optimal temperature for the next step, then move toward welding. The radial axial machine drives the first transformation of the ring blank. Welding of the blocks is followed by integration into modular sections, forming the vessel's backbone. Heating the blank sets the stage for shaping operations that follow. The assembly line begins with aligning the raw materials and proceeds with outfitting modules with piping and lab systems. The vessel includes 4 scientific labs, extensive piping over 10 kilometers serving more than 20 systems, and over 130,000 individual parts. Once structurally complete, the ship is launched and proceeds through systems commissioning and sea trials before final delivery. Each step conveys a surge of pride. This ship is a powerful testament to skilled hands and collaborative passion. Strength and precision of industry meet inside a controlled environment where every pipe is shaped for reliability. This is the fabrication of API 1104 pipe sections for a natural gas compressor station, showcasing how discipline and skill create dependable infrastructure. Preparation of pipe segments opens the sequence. Steel is stored indoors, kept clean before fabrication begins. Cutting then follows as automated plasma tables program exact lengths and bevels. The blank undergoes its first transformation when positioners rotate the heavy sections with minimal manpower. Welding marks the next stage. Certified procedures, 23 in total, govern each pass. Preheating the joint sets the stage for strong bonding. Submerged arc welding then drives speed and quality, with fit-up verified by digital levels to ensure accuracy. Final phases highlight inspection and tracking. Each weld is reviewed, measured, and logged within the 24/7 monitoring system. The outcome is dependable piping shaped by discipline and teamwork. The scale of copper production ignites respect for the blend of power and control that defines this plant. At Bohr, automation and engineering converge to deliver copper through an intricate series of operations. Ore preparation initiates the production sequence, moving material by conveyors into the smelter. Concentrate and catalysts reach the flash furnace, where intense heat begins the first transformation. Inside Pierce-Smith converters, copper content rises from 65% to 98%. The molten metal then flows into the anode furnace, where weighing ensures accurate casting. Each anode plate emerges through a turning and transfer system designed for continuous flow. Final phases emphasize environmental control, cooling towers driven by frequency inverters, and wastewater neutralization plants governed by PLC and HM. I keep the operation reliable and sustainable. Powerful rollers strip armored cables, separating cores with efficiency and remarkable consistency. Endurance in engineering often reveals itself when machinery is rebuilt, not when it is first created. In this sequence, an overhauled Frick rotary screw compressor model YCCH 2331 is brought back to life through a detailed reassembly. Every piece regains its role in a machine designed for endurance. Assembly begins with the rotor pair, the heart of the compressor. Their interlocking profiles ensure compression, and once aligned, they set the rhythm for all subsequent parts. Cylindrical roller bearings and ball bearings follow, each one providing support for high-speed rotation. The contrast between the delicate shapes of the bearings and the heavy rotors highlights the balance required in design. It is impressive to see how stability relies on these hidden elements. The process continues with seals and distance rings. The shaft seal, supported by a housing spacer and cover, protects the internal system from leaks. Springs and washers add tension, while a bearing backup plate and adjusting washer secure alignment. At this stage, the compressor already reveals how small parts define big performance. The sequence conveys how order and function are inseparable in machinery. Attention then shifts to sleeves and balance components. Distance sleeves, piston sleeves, and male balance pistons take their place, ensuring equal load distribution during operation. The female inlet bore cover and the unloader spring integrate next, helping regulate airflow within the cylinder. The addition of each unit makes the compressor feel closer to completion. The cylinder assembly marks another stage. Internal cylinders, lock washers, and lock nuts secure the framework, while a cylinder cover with helical rod stabilizes the moving system. At this point, the compressor begins to resemble its final form. Momentum builds as the structure becomes more recognizable. Final touches include installing backup plates, seegers, and fastening washers that bind all components firmly. Once tightened, the system holds a compact but powerful core. Certification marks highlight compliance with marine refrigeration standards, ensuring safe and reliable service. The sense of readiness at this stage is undeniable. When the last elements are in place, the reassembled compressor stands as a renewed unit ready to serve demanding applications. What once was a collection of parts now embodies strength and purpose. Gigantic castings, reaching hundreds of tons, demand flawless processes to achieve shape and strength. Production begins with model creation, followed by forming molds while molten metal is prepared. Pouring unites form and alloy, producing massive structures. Grinding, blasting, and measuring refine results. With Zeiss ATOS LRX scanning, geometry becomes fully digital. Each step shows how tradition and technology meet challenges of scale with striking efficiency. Electric power must travel great distances, and submarine cables make that possible. Creating such a cable involves a series of technical stages that transform raw conductors into a robust product ready for the sea. It begins with conductor manufacturing, where strands are produced and twisted together. Stranding machines at this facility are among the fastest of their kind, enabling production on a remarkable scale. Next is extrusion, where insulation is applied. Heating pipes stabilize the material, cooling pipes solidify it, and the world's largest chamber maintains extremely long continuous lengths on massive 450-ton reels. Watching insulation bond seamlessly is truly impressive. The cable then passes through a lead press, adding a watertight sheath. A further protective layer is applied in the following extruder before the product is coiled onto turntables with capacities up to 1,000 tons. At this point, stranding with 3 main lengths, plus fiber optic lines, ensures functionality. Later, the armoring stage applies steel wires of 6 to 8 millimeters, giving the cable the ability to withstand enormous pulling forces. The finishing section wraps it with bitumen-soaked materials, completing the mechanical protection. The engineering logic behind each layer is fascinating. Once prepared, the cable is transferred over a special bridge nearly 2 kilometers long. 8 pulling units, with speed and tension carefully managed, guide it across without bending or stress. After traveling about 25 kilometers, it reaches the river port. There, reels are loaded onto pontoons and secured for transport. Finally, in Rotterdam, the cargo is moved directly onto a laying vessel. The outcome is a 30-centimeter thick submarine cable, thousands of tons heavy, capable of transmitting renewable energy from offshore wind farms to consumers. Each stage demonstrates a powerful combination of industrial skill and technical mastery. At PT Indal Aluminium Industry, the journey of aluminium begins with extrusion, where heated billets are forced through dies to form precise profiles. The glow of the hot metal gives the workshop an energetic atmosphere. These profiles are then anodized, creating a durable surface layer that resists corrosion. Each stage shows how strength and beauty can exist together in one material. Painting follows, adding both color and protection for long-lasting performance. There's a quiet rhythm as machines and people interact smoothly. Fabrication shapes components for windows, doors, solar panels, and more. The scale of production reveals impressive versatility. Finally, assembly integrates parts into complete products, ready for global markets. Every finished piece reflects dedication and vision. A towering steel pole standing on a roadside at night seems ordinary, yet its creation is a story of engineering and endurance. At Sokoyo, the journey begins with raw steel plates, selected for thickness and durability. Large sections are measured, cut, and prepared for shaping, ensuring each piece can withstand outdoor conditions for many years. The first stage is plate cutting. Using automated plasma or flame cutters, the steel is divided into precise segments according to design. These segments will later form the cylindrical body of the pole. It is striking to observe how heat and flame slice through metal so swiftly, creating clean sections ready for the next stage. The second stage is rolling. The flat plates are guided through heavy rollers that bend them gradually into a rounded profile. Each pass tightens the curvature until a complete cylinder is achieved. The rolling process feels powerful, as thick steel sheets bend smoothly into controlled arcs. The edges are then aligned in preparation for welding. The third stage is welding. Automated submerged arc welding machines join the seams, creating solid, continuous joints along the length of the pole. The welds provide structural strength, ensuring the pole can stand against wind and environmental stress. Watching sparks shower across the metal leaves a strong impression of energy and motion. Then, the poles are fitted with brackets, flanges, or mounting points for solar streetlights. The next stage is straightening and inspection. Hydraulic presses adjust any deviation, while technicians confirm alignment and roundness. The pole's surface is then ground to remove excess welds or imperfections. At this point, one begins to see the pole emerge with balance and symmetry. The following stage is galvanizing. Poles are dipped into molten zinc, coating every surface to prevent corrosion. This protective layer extends service life in harsh climates. The shimmering finish gives each pole both resilience and a sense of completeness. Each finished product represents a combination of strength, endurance, and practical design. There is a quiet satisfaction knowing these poles will guide light along countless roads. An immovable block of steel is soon confronted by blazing heat and relentless force. At Walzen Arl, thick ingots are heated until glowing red. They are then pressed and elongated, shaping the massive roll body. The glow of hot steel creates an atmosphere both intense and inspiring. Next comes machining, where lathes cut surfaces to exact dimensions. Grinding smooths every contour. Finally, inspection ensures durability. Each completed roll feels like strength captured in metal. Steel may appear cold and lifeless, yet under the right process it becomes something remarkable. The workshop in Dubai shows how large pressure vessels are made, revealing each stage that transforms raw material into durable structures. The sheer scale of these components instantly commands respect, as tons of steel are moved and formed. The process starts with rolling flat plates into curved shells. Powerful rollers bend the thick metal until it takes on the rounded form needed for vessel walls. Conical sections are also produced, giving shape to the tapered ends. The sound of steel moving through rollers gives an impression of strength meeting purpose. Sparks and molten metal seal the connection, turning separate edges into one continuous surface. Next comes fit-up, where shells and cones are aligned with precision before welding. The sections are adjusted carefully to ensure smooth joints and exact dimensions. Every adjustment here reflects the workers, focused on accuracy and reliability. Welding follows, using the submerged arc welding ATOS method. A column and boom manipulator guides the process, allowing deep, consistent welds along the massive seam. This creates joints strong enough to withstand extreme pressures once the vessel is in operation. It is striking to see how controlled movement and advanced tools combine so seamlessly in this stage. As the vessel grows in size, each ring and cone joins the next, building the structure step by step. The result is a towering cylinder capable of handling demanding industrial applications.